we're going to be talking about binary search tree deletion, the most complex of the three primary operations on binary search trees. So if you don't know what a binary search tree is and you want to learn, you can click the title card in the top right-hand corner to view our video on binary search trees. But we're going to assume that you've already watched that and came over here. So the first thing you need to do when you're discussing deletion is learn what it means, the min and max of a tree. The min of a tree is the smallest node in the tree. Using the binary search tree property, the min we know to be the leftmost node in that tree. Now, the max of a tree is the largest node in the tree. Using the binary search tree property once again, we know that to be the rightmost node in the tree. Next, we have to define two more concepts, the successor and the predecessor of a node. The successor of a node is the next largest node in the tree. And the predecessor of a node is the next smallest node in the tree. So looking at our example on the left, we see that the minimum of this tree is 10 by tracing down the left side of the tree. Now, by tracing down the right side of the tree, we see that the maximum is 80. If we look at the node 50, we can find that the successor of 50 is 55, since 55 is the next largest number in the tree. And the predecessor of 50 is 35, since 35 is the next smallest number in the tree. So now that we understand these concepts, we can look at the algorithms for min and max. So in a binary search tree, as we said, the min is just the leftmost node. So what we're going to do is just traverse down the left side of the tree until our left child is null, in which case we're going to return the current node we're at, since that is the minimum. On the other hand, if we're looking for the max, we know that we can just traverse down the right side of the tree and return the node once our right child is null. So now that we've looked at the algorithms for min and max, we can now start discussing deletion. So in deletion, there are three primary cases and one edge case. The edge case, which we'll call case 0, is when the node that we are searching for to delete does not exist within the tree. In that case, we are going to do nothing. Now, the real cases begin. So in case 1, if the node we're looking to delete is a leaf, we're simply going to delete that node once we find it. So for example, on the tree on the left, we're going to traverse down the tree using binary search tree search-like algorithm until we find the node we're looking for, which is 35. So we will move left of 50, right of 20, right of 30, reach our node 35, notice that it's a leaf node, and just remove it from the tree. Now case 2. Case 2 is when our node that we're trying to delete has one child. When it has one child, we just simply replace the node that we're trying to delete with its one child. So in our example in the middle, we're going to delete the node 30 from the tree. So once again, we search for it similarly to search in a binary search tree. We're going to move left of 50 and then right of 20. And then once we're here, we're going to delete that node and replace it with its right child, this case being 35. And then we, of course, delete 35 from the tree. And lastly is case 3, the most complicated case, and the one that has a little bit of subtlety to it. So there are two options we can take when we're talking about case 3. Either we're going to replace the node that we're looking for with its successor, or replace it with its predecessor. The reason we have to do this is because in case 3, the node we're trying to delete has 2 children. And if it has 2 children, we cannot simply replace it with either its left or its right, because then we have no place to put the other child. So in the case 3 on the right side of the screen, if we were to delete 50, here, of course, we're going to use successors instead of predecessors. So to delete 50, we're going to look for its successor, which we already know is 55 from above, as we already computed it. And we're going to replace 50 with its successor, 55. Next, now we have this extra node in the tree, 55, so we need to delete that. So we're going to call our binary search tree deletion once again, but this time on 55 and remove it from the tree. So now that we've talked about the intuition behind deletion, let's take a look at the algorithm. So the binary search tree deletion algorithm takes two parameters. It takes a node to delete, which will denote V, and a current root, so the current root that we are looking at. And this algorithm returns a node. So if the current root we are looking at is null, this implies that we either didn't find the node that we wanted to delete, or we've already found it and are now currently deleting it. So this is case 1, or in some cases, this is case 0. It handles both. On the other hand, if the data inside of our node we are looking to delete is smaller than our current root's data and not equal, we're going to have to traverse leftwards. We're going to recursively call binary search tree delete on the right subtree and the left subtree. And we're going to set the left subtree to be that recursive calls return. Now, in the other case, if the data inside of our node is greater than the data inside of our root, we are going to set the right subtree of our current root to be the binary search tree deletion recursive call of our same node and the right of our current root. So now brings us to case number 2. So in case number 2, we have either a left child or a right child, and we've reached the node we're looking to delete. Since we've passed part 1, and the first if statement and the second if statement, that being that our data is less than r.data and v.data is greater than r.data, we know that v.data at this point is equal to r.data. So if we have no left child, we're just going to replace it with our right child by returning r.right and allowing the recursive calls to finish. On the other hand, if we have no right child, we're just going to replace it with our left child. Finally, this brings us to case number 3. Now, case number 3 is a little more complicated than the other two cases, but not that much more once we've defined successor, min, and the other notation that we needed for this. So the first thing we're going to do is find the successor of the node that we want to delete. Because we know that our node has both a right child and a left child, we know that the successor is just the minimum in its right subtree. So we're going to use the BST minimum algorithm from above. Next, we're going to swap the data in our current root with the data inside of the successor. Finally, we're going to call binary search tree deletion on the successor inside of the right subtree. So there's two things to note here. First, we are swapping data. Yes, usually you do not want to swap data. You want to just manipulate pointers. However, it is implied in this case that if you wanted to, you could easily change this to manipulate pointers instead of swap data. And just for the sake of brevity and for clarity, we are just going to swap the data here, but the idea is the same. And second of all, notice that we take binary search tree deletion of the right subtree. This is because we've already swapped the data. So if we call binary search tree deletion on the current root, we might have some unintended side effects, such as deleting that root that we just created. So last thing we need to talk about here is the runtime of binary search tree deletion. Now, the runtime, just like insertion and just like search, is going to be linear in the worst case being we are just working on a linked list, or O of n as we say. And in the average case, when the tree is balanced, our runtime is going to be O of log n, or logarithmic. So that wraps up our discussion about binary search tree deletion. If you like this video, please hit the like button down below. Leave a comment if you want to see a specific video or you want some algorithm explained. On the other hand, we have 2 other videos about binary search trees: insertion, search, and just an introduction. If you haven't seen those already, I recommend you go watch those to get a full understanding of binary search trees. Otherwise, I hope you enjoyed, and we'll see you in the next video.